right, guys, next section, water. So I'm going to represent water with my little water molecule. Hydrogen is the white, oxygen is the red. Water in living things. Water is the most abundant molecule in living organisms. 60 to 70% of your total body weight, and in most other organisms as well, is made up of water. It is called a polar molecule because the electrons spend more time circulating the larger oxygen atom than the smaller hydrogen atoms. So the oxygen atom will have a slightly negative charge. Your hydrogen atoms will have a slightly positive charge. So you have a positive pole on your hydrogen end and a negative pole on your oxygen end, which creates a polar molecule. Hydrogen bonds occur when covalent hydrogen is positive and is attracted to the negative oxygen of an atom some distance away. So it's not a true bond. We're not sharing or exchanging electrons, but we are acting like magnets. And it's a dotted line because it's weak. It can be pretty easily broken if you just rub it in your hand. It breaks just like water will evaporate if you rub it between your hands. But it does tend to give it some special properties which allow it to be key in life. The first one, it says water is cohesive. This is the property of clinging together. It creates surface tension, which forms a meniscus, which is a curved shape, and therefore it can fill vessels such as blood vessels. So if you put a bunch of water molecules together, it will kind of make a dome, and it will cause that water to form a droplet, basically. It makes it stick together. Water is a liquid at room temperature. Most low molecular mass compounds are gases. Oxygen has O2 has an atomic mass of 32, and it's a gas. But water is a liquid, and its atomic mass is 18 AMUs. So even though water's atomic mass is lower than other gases, it's still a liquid at room temperature. It will boil at 100 degrees Celsius. That's where it turns into the gas, so it's got a higher point of vaporization, or lower point of vaporization, sorry, and it freezes at 0 degrees Celsius, which is where it becomes solid or ice. Another thing you need to know about water is it is a solvent, universal solvent for polar and ionic molecules, therefore helping chemical reactions outside and within our bodies. So if you look at the next page, or this page, it says that hydrophilic are ions and molecules that do interact with water. So this represents chlorine, this represents sodium, and they stick together. I just made table salt in my hand. And this represents my water. So what happens when you have your universal solvent is sodium's positively charged. It will be attracted to the negatively charged areas on the oxygen, and the water will actually kind of split it apart and form around it. And the same thing that will happen with the chlorine is the positive parts of the water will form around it and will kind of mesh around these and dissolve in water. So that's how ions will be dissolving in water. Sugar will pretty much do the same thing. Positive and negative parts on the sugar will be attracted to the positive and negative parts in the water. However, this represents CH, should be 6, but I'm missing one of my non-polar groups here. And so CH4, CH6 are non-polar molecules. They are carbon rings. And so if you try to stick them to water, it's just, there's nowhere that will stick. It will not work. So these are hydrophobic, which are non-ionized, and non-polar substances. They do not react with water. So your fats, your lipids, oil and water, it separates. They feel slippery. Those are things that do not interact with water. Number 4, the temperature of liquid water rises and falls slowly, preventing sudden or drastic changes, which is super good. You don't want your bodies, if they get a little heated, to like suddenly turn into gas and evaporate. That's not how our bodies would run well. So thankfully, we rise slowly. We retain heat and we lose heat on a slow basis. It says, a calorie of heat energy is the amount required to raise the temperature of water 1 gram of water 1 degree Celsius. So 1 calorie equals 1,000 calories. Should be 1 kilocalorie. I don't know why that isn't right. 1 kilocalorie, K-I-L-O, is 1,000 calories. Water in large bodies changes temperature slowly and acts as a temperature buffer. Oh, I know what Mr. Johnson meant. Sorry. I am totally trying to read his notes. So 1 calorie of heat energy is what's required. It takes 1,000 calories to burn 1 calorie of heat energy. That's what he's talking about. I'm sorry, it took me a second to look at that. I even read it ahead of time and thought I knew, but it just occurred to me. Last little bit, evaporation is changing water from a liquid to a gas. It requires 540 calories. Therefore, it uses excess heat in the body, thus cooling it down. So you have to heat up water. That's why when you sweat, it will evaporate because you're heating it from the skin. So evaporation is a cooling process. And your last blank for water is frozen water or ice is less dense than liquid water. So ice floats on water. Most solids are more dense than their liquid or their gas forms, but water is the opposite. Frozen water is less dense than liquid water. So water is most dense at 4 degrees Celsius when the water molecules have contracted. So colder water will sink before it becomes ice. At temperatures below 4 degrees Celsius, remember at 0 is when it becomes ice. At temperature below 4 degrees Celsius, hydrogen bonding becomes more open, making the ice less dense. So the hydrogen bonds will kind of split a little further apart, making the ice less dense. And ponds and lakes freeze from the top down, which protects aquatic organisms. So again, cool water before it becomes ice sinks, and so it keeps the aquatic organisms from freezing. The other thing that's not in your notes is, or describing cohesion, is capillary action. So capillary action is what allows water to climb trees. So this is an example of how capillary action would work. One molecule sticks to the other. This is cohesion. And then adhesion is the ability of these to stick to other surfaces. So other charged surfaces, such as my paperclip, will stick to this. It will also stick to vessels in your body or the xylem in trees. So adhesion is what allows it to stick to other surfaces. Cohesion is what allows it to stick to itself. So that's the other number 7 that wasn't in your notes. All right, I'm going to stop it and pick back up with acids and bases next.